A.S. Falmari. In the last video, we have discussed the procedure of simplex method. Now, in this video, we are going to discuss some problems using simplex method. Learning outcome of today's session is at the end of the session, students will be able to solve the optimization problems of real life using simplex method. Consider the first question. Use the simplex method to solve the linear programming problem maximize z equal to 3x1 plus 5x2 plus 4x3 subject to the constraints. These are the three constraints provided and the three variables x1, x2, x3 are non-negative. Now the solution. So we know that the step number 1 contains two things, verifying whether the given linear programming problem is of maximization type, and the second one is verifying whether all the right hand side constants present in the every constraint is positive or not. Here you can see that the given linear programming problem is a maximization type. So the first thing is done. The second thing, verifying right hand side constants present in every constraint are positive or not. In the first constraint, we can see that 8 is present, which is positive. In the second constraint, it is 10, which is also positive. For the third constraint, 15, means we can say that all the right hand side constants present in the constraints are positive. So the step number 1 is over. Now the step number 2 is of obtaining the standard form of this linear programming problem. So obviously we have to write this maximize z objective function as it is. Now here constraints are of the type less than or equal to. We can convert all these inequalities to equalities by adding the slack variable to the left hand side. In the first equation we can add s1, in the second we can add s2, and in the third constraint we can add s3, and all these inequalities can be converted to equalities. So after adding the slack variables, our standard form will look like this: maximize z equal to 3x1 plus 5x2 plus 4x3 plus 0 into s1 plus 0 into s2 plus 0 into s3, and subject to the equality constraints. Now moving towards step number 3, which is of setting up initial basic feasible solution. To obtain initial basic feasible solution, we are going to substitute the values of x1, x2, x3 as 0 and getting the values of s1, s2, s3 as the right hand side constants 8, 10, 15 respectively. So this is our initial basic feasible solution. x1, x2, x3 are called the non-basic variables. s1, s2, s3 are called the basic variables. Now moving towards the next step, that is setting up initial simplex table. The first column obviously of the basic variables. So the basic variables are s1, s2, s3. Now their coefficients in the objective function are 0. And the values of these basic variables in the initial basic feasible solution are 10, 18, 15 respectively. Now we can list all the variables present in our linear programming problem, and we can write at the top the coefficients of these variables in the objective function. First of all, we can take a first constraint and write down their coefficients x1 to s3. Like this. Then we can take second constraint, equality constraint, and write down their coefficients as a second row. Then the third row will be the coefficients of the constraint third. Now once we set up this body matrix, the next job is of calculating a zj row, that is the sum of the product of CB column and the xj column. In the initial simplex table, always we are having the coefficients of the slack variables as 0, which means that when we multiply by 0 to any non-zero number, again it results in 0. That's why in the initial simplex table, the zj entries are always 0. Now once you have Zj entry, then we are going to calculate delta j entry, which is the subtraction of coefficients of the variables in the objective function minus this Zj rho. So after taking their subtraction, we get the delta j entries like 3, 5, 4, 0, 0, 0. In the delta j row, we can see that there are 3 entries which are positive. It is indicating that whatever the initial solution we are having, that is not optimal. For the improvement, we are going to remove one variable from this basis and we are going to introduce a new variable. We know that the incoming variable is the variable associated to largest delta j entry. Among these 3 positive entries, 5, 1 is the largest delta j entry. Hence, we can mark it by upward arrow and the corresponding column is called as key column and the variable associated to this column is x2. So, the meaning is x2 is going to enter this basis. To find who is going to leave, we have to calculate minimum ratio, which is the ratio of xb column and the key column. Now taking the ratio of xb column and this key column x2, we are getting the minimum ratios are like 8 by 3, 5 and 15 by 2. All are positive and among these two, the minimum one will be the 8 by 3. So that's why this row is called as a key row and the variable associated in the basis for this key row will leave the basis. That is, S1 is going to leave the basis and X2 is going to take the position of S1. So in the modified simplex table, what we are going to do, we are going to introduce at the first position a new variable x2 and we are going to remove this s1 and then we are going to write down here the coefficient of this x2 in the objective function, which is 5, and then we know that an element lying at the intersection of this key column and key row, which is 3, called as a key element. We are going to convert this 3 to unity by dividing this full row by 3, and after converting it to 1, we are going to convert the elements lying below of that key element to 0 using this key row and by applying a suitable row transformation. To convert this 3 to 1, we are going to divide this row number 1 by 3, and to convert this 2 to 0, we are going to use a transformation like R2 changes to R2 minus 3 by 2 R1, and to convert this third entry 2 to 0 using row number 1, we are going to perform the transformation R3 changes to R3 minus 2 by 3 R1. After using these 3 transformations, we get a new simplex modified simplex table as like this. So once we convert key element to 1 and the elements lying below of that key element to 0, the next step is of finding the values of Zj row. We know that the Zj is what? The sum of the product of Cb column and the corresponding Xj column. In the Cb column, you can see that out of 3 entries, 2 entries are 0 and 1 entry is non-negative. So there is no need to take the product of all these 3 entries with the Xj column. Simply we can multiply the first entry to the first entry of that respective Xj column to get that Zj entry. So this 5 into 2 by 3, that will be 10 by 3, 5 into 1 is 5, 5 into 0 will be 0, 5 into this 1 by 3 is 5 by 3, and 5 into these 2 zeros will be 0 and 0. The next step, calculating the net evaluations delta j, that is taking the subtraction Cj minus this Zj. After taking the subtraction, we are getting these entries. Here you can see that there is only one positive entry exists, which is indicating that the current solution is also not feasible, not optimal. So as we are having only one positive entry, so this will be the treated as largest delta J positive entry. We can mark it by upward arrow. We can write it as a key column. The variable corresponding to this column is x3. So x3 will enter the basis. Now to find out the outgoing variable, we can take the division of xb column and this x3 column, which leads to, see, obviously here we are writing dash because the first xb entry is 8 by 3 and x3 entry is 0. So we are getting infinity. Negative values or infinite values are not written here. Only the positive entries we are going to write in minimum ratio column. Among these two, 14 by 15 will be the smallest one. So this will be the key row and its associated variable is S2, that is going to leave the basis. Here the key element is 5. Now we have to convert the elements lying above and below of that key element to 0 and convert the key element to 1 by using a suitable transformation. After applying these two transformations, we get this new modified simplex table. In this delta J, we can see that again one positive entry is exists, which is indicating that again some improvement is possible in the solution. So this column will represent a key column and this x1 will enter the basis. To find out the outgoing variable, we have calculated the minimum ratios here. Among these two, 89 by 41 will be the smallest one. Variable corresponding to this key row will be the S3. It is going to leave our basis. Then again we have to perform the same steps, converting key element to 1 and the elements lying above of that key element to 0 by using suitable row transformations of this type. After performing these row transformations, we are having this new simplex table. In this delta J, all are negative or 0, means no positive entry exists here. The meaning is we have reached up to the optimal solution. That required optimal solution is what? X2 has the value 50 by 41, X3 has the value 62 by 41 and X1 has the value 89 by 41. And at these values of x1, x2, x3, the value of the objective function is calculated here. It is our optimal value of the objective function.